We continue our recapitulation of the eigenvalue-eigenvector equations by now looking for the eigenvectors for the matrix B here. Recall that we found two eigenvalues. We found lambda 1 was 8 and lambda 2 was -2, and there were two of them because we had a 2 by 2 matrix. Then the eigenvectors have to go with a specific eigenvalue. So what we're going to do is look at one of the eigenvalues first and the other one next. And we have to remember our eigenvector condition. And the eigenvector condition is similar to the eigenvalue one, just one step without the determinant. It's that b minus lambda I, so that same construction, but this time times a vector equals 0, and we're looking for that vector v. And in fact, because this is 2 by 2, let's let that vector have two elements a and b, and we're going to solve for a and b. All right, let's apply that condition for lambda 1 equals 8. So b minus lambda I times v is going to equal 7, 3, 3 minus 1. Then we subtract this specific value down the diagonals and multiply it by our vector v, which is what we're looking for. So we put our numbers in there, a, b. I guess they're letters, technically. Then we subtract this all out, and we're going to get -1, 3, 3, -9 times a and b. And remember, at this stage, you can freeze frame for a second, and you're going to check that this is not invertible. And remember, that's a good thing. Why is that a good thing? Because we're setting that equal to the 0 vector. Sorry, that should have been a 0 vector here earlier. I apologize. We're setting this equal to the 0 vector. And if this matrix is invertible, then there's one solution to the system of equations, and it would be the 0 vector for our eigenvector. Well, we're talking about vectors that get scaled by our matrix. I don't want a 0 vector. If the only answer is a 0 vector, I've done something wrong. But we have not done something wrong. There's going to be lots of solutions to this equation, and they're going to include interesting vectors that we're going to hold on to, and in fact define as our eigenvectors. So because we see these scaled columns or scaled rows, we know it's not invertible, we can just grab either one of these rows and get an equation out of that. And this says that, say, a is equal to 3b. And remember, this is an element of arbitrariness here. We can pick, let's say, pick b equals 1. That will mean that a has to equal 3. And then that means our v1, the vector that goes with lambda 1, would be 3, 1. So 3, 1 is an eigenvector for lambda 1 equals, or corresponding to lambda 1 equals 8. All right, we did that once. We're going to repeat that on the next page, taking a little less time on it. For lambda 2, which was -2, we again build our b minus lambda I times v construction. We take the b matrix here, 7, 3, 3, -1, and we subtract -2. I do try to do this in gory detail, even if I'm doing it myself by hand, because it's really easy to make silly sign mistakes. And we do that times AB, and that, when we tidy it up, is 7 plus 2 is 9, 3, 3, minus 1 plus 2 is 1. Like, oh, good. Phew. If we take a look at that matrix, we can see that this row is a multiple of that one. So we have our check again, that it's not invertible. And we set that equal to 0, 0. b minus lambda I times our vector has to equal the 0 vector. All right, let's grab the second row this time. 3a plus b equals 0, or b equals -3a. So we can pick, let's pick a equals 1. That would give us b equals -3. So v2 as 1, -3 is an eigenvector for lambda 2 equals -2. Now, I like picking 1 values, especially if we carefully craft it, but it's worth noting we could pick a equals -7 if we wanted. That would tell us that b is equal to -3 times that, which is positive 21. So v2 equals -721 is also an eigenvector for lambda 2 equals -2. Now, for some people, that's totally fine. For some people, though, it just feels weird in a math class to say, yeah, just pick a number, whatever. They naturally get caught up in the seeming arbitrariness of the eigenvector construction. Why do we pick just one vector as the eigenvector when there are, and there have to be, an infinite number available? Well, for those people, I say, we have terminology that's probably more suited to what you're thinking. The more elegant approach is to define the eigenspace, which is really what we care about. For an n by n matrix with this particular eigenvalue, so this is going to be tied to an eigenvalue like our eigenvectors are, there's a vector subspace of Rn given by the kernel of a minus lambda I, which is the same thing as saying a minus lambda I, sorry, it's all v's, which satisfy a minus lambda iv equals the 0 vector. And we call that collection, that space, the eigenspace associated with that eigenvalue. So how does that look different? Well, for the matrix B we just saw a second ago, for lambda 1 equals 8, we would say that the eigenspace is, let's call it E1, and it's a set of x and y's in R2. Actually, let's put them vertically here. It's a set of x, y's in R2 such that, well, we actually had a restriction. Let's just go back a couple of pages here. For lambda 1 equals 8, we had that a equals 3b, or that x equals 3y, such that x equals 3y's. Let's just repeat that for lambda 2 here. The eigenspace is E2, which is the set of x and y's in R2, such that, well, what was it for these guys? This was, b was minus 3a's. This is the x's, that's the y's, so y is minus 3x. And this is going way back, like 4 or 5 weeks ago. We looked at these kinds of constructions and we said, well, these are lines, right? All the points that satisfy x equals 3y are x equals 3y. It was like 3, 1. So that's this space here. This would be E1. Label our axes here, x and y. All the points on this line, all the points on this subspace are members of this eigenspace. Any vector in this space, when we multiply it by b, is going to just get scaled. Likewise, this lambda 2 equals -2, that's a different line. Turns out it's perpendicular and it looks like that. All the vectors along that line would be scaled by -2 if we apply the B matrix to them. But again, we have this entire line is really what is scaled by this eigenvalue here, not just specific vectors. So let's just do a quick compare and contrast of eigenspaces versus eigenvectors. And we'll just do it, for example, for the first eigenvalue. It's going to be the same for both the constructions, but the eigenspace, highlight the space part here, is equal to all the vectors with x equals 3y. The eigenvector that we found, which was 3, 1, is a basis for the eigenspace. So we're getting these same ideas coming back over and over. We can either think of the eigenspace as the entire line, or we can say, well, once I know what 3, 1 is, and I know I'm allowed to use linear combinations, then maybe this is actually just as informative and easier to understand. And to tie those two together, the eigenspace then is the span of the vector 3, 1 here. So the eigenspace is the span of this vector. So basis, building block vector, through the span gives us all the possible elements that are in the space. And we do all the same description just with the different vectors. And similarly, for the other eigenvalue, lambda 2 equals -2. The eigenspace would be all the vectors that satisfy its relationship. The eigenvector that we found, one of them would be enough to be a basis for it. If we take that basis, find its span, that is the space, and we get back to that same relationship. So that example took us a bit deeper into the terminology that is frequently used around eigenvectors and eigenvalues. It's not just the values and the vectors. There's the other idea of the characteristic polynomial along the way, and the eigenspaces as a complement in some ways to the eigenvector descriptions. There's no new ideas there, but the nomenclature can sometimes trip students up, and sometimes it's helpful to have the alternatives available.